9.4, example 5. In this example, we're going to go ahead and try to determine the convergence of a series. So we want to determine the convergence of this series, 3 to the n divided by 5 to the n plus 1. Now, when you work with series, you should try to trust your gut. So I look at this right here and I go, well, my denominator is going to grow much faster than my numerator. So I think it's going to converge. So I think that this thing is going to go ahead and converge because the denominator is larger than the numerator. It's just good to start thinking that way. Even though we're going to actually figure it out, it's just good to think that way. All right, so we're going to go ahead and do the test. So you do the limit as n goes to infinity, absolute value a sub n plus 1 divided by a sub n. So we get that this is, we're going to need some space. So the limit as n goes to infinity. So the first thing I do is I'm going to write a sub n plus 1. So it's 3 to the n plus 1 divided by 5 to the n plus 1 plus 1. And then all divided by 3 to the n divided by 5 to the n plus 1 with big absolute value bars around the whole thing. So this becomes the limit as n goes to infinity. And absolute value bar 3 to the n times 3 over 5 to the n times 5 plus 1 times 5 to the n plus 1 over 3 to the n. And the reason I do this is I'm multiplying by the reciprocal of this here. Okay, so let's see if we can cancel anything off. Well, I can cancel off this, so that's nice. And I can bring this 3 out of the limit because it's a constant. So this is 3 limit as n goes to infinity, absolute value 5 to the n plus 1 over 5 to the n times 5 plus 1. Now, this one's a little tricky because I need to get basically these the same, and I'll be good to go. So I'm going to use my n behavior model, and it becomes 3 limit as n approaches infinity of 5 to the n divided by 5 times 5 to the n. Because the plus 1s really don't do anything when you go to infinity. So these 5 to the n's cancel. So I'm left just with 1 over 5. So this is 3 times the limit as n goes to infinity of 1/5, which is just 1/5. So my answer is 3 over 5. Since 3/5 is less than 1, the series will converge everywhere. There's nowhere, no x value to worry about because we get a constant and we don't have to solve for x. The series converges for all x's. Okay, on your own, I want you to determine if this series converges. All right, so let's give it a go. So I'm going to try that ratio test. So it's the limit as n goes to infinity, absolute value a sub n plus 1 divided by a sub n. So now we just got to write it all out. So we get the limit as n approaches infinity of n plus 1 squared minus 1 divided by 2 to the n plus 1, all divided by n squared minus 1 divided by 2 to the n. Notice I just replaced the n with an n plus 1. Okay, so let's clean that up because this is just not pretty to look at. So I'm going to write this as n squared plus 2n plus 1 minus 1 divided by 2 to the n times 2. Then do two things at once. I'm going to also multiply by the reciprocal. So the 2n's cancel. This 2 can come out. So I'll go ahead and pull that 2 out, but it's in the denominator, so it's 1/2 limit as n goes to infinity, absolute value of n squared plus 2n divided by n squared minus 1. So notice that if I use an n behavior model, my highest powers are both n squared with coefficients of 1. So this whole thing is going to go to 1. So the entire thing is equal to 1/2, which is strictly less than 1. Therefore, the series will converge everywhere.